Anything? 740. Thank you. This is sort of a classic setup here. All right. So this is a pretty good problem because it's going to really showcase several things that you have to know. The very first thing I want to say is when they're giving these type of problems, there are common terms that they use. One of the things is the line voltage. Here it's 480 volts. Now by that, hope you can see that, plus to minus 480 volts at 0 degrees. That's the voltage that the actual company's operating at. It's an industrial load at 480 volts. For us, the line voltage would be 120 volts at the wall here. Now the power company is sending a higher voltage because the lines or the connecting lines, electrical lines, are going to have some loss. Does that make sense to everybody? But they have to make sure that this line is going to operate at the proper voltages because all equipment is designed with an assumption that the voltage at the wall outlet or whatever at the industrial three-phase supply will be the same everywhere. It'll be specified either 480 or 120. That's critical. Now here he gives us information. And he's looking for the power factor here. Before I get the power factor at the source, I'm going to get the voltage at the source. But I want to make sure you see all aspects of this. And you need to be attentive here if you missed the class or haven't been keeping up. So first, when we talk about power factor in general, the power factor is equal to the cosine of theta v minus theta I. That's all it is. The problem with just stating the power factor by itself is cosine is an even function, so cosine of x is the same thing as cosine of minus x. Said a different way, the cosine of 30 degrees is the same thing as the cosine of minus 30 degrees. I hope I made that clear to everybody. So they have to do one more thing. They use the term lag or lead. Lag, and I think I mentioned this last time, I talked about Eli the Iceman. Y'all remember that? How many do from last time? This is an old saying. When I was in high school, I remember hearing it. One person heard it in here. L is the symbol for inductance. It's everywhere. Doesn't matter if you're in England or here. C is the symbol for a capacitor. Now, a difference is in England and in some areas, E is the symbol for voltage, and I is the symbol for current. So when they say Eli, here you see E, or voltage, is ahead of current. You all see this? When voltage is ahead of current, the current is lagging, or the power factor is lagging. And I'm going to go through this. You remember me talking about this, right? If it's leading, which is extremely rare, then that means that the actual voltage has an angle that's ahead of the current angle. And some of this is going to have to be made clear with examples. Now, the reason I'm going to tell you this, how many are industrial engineers in here? Anybody? All right, a couple. In mechanical too, but really in industrial engineers back at least in the day, when they had large textile mills and all that, they had to worry about the power factor of the mill. The mill primarily had large rotating machines that were electrically driven. They have an enormous amount of inductance. You're just going to have to take my word on that. Whenever there's a lot of current and magnetic fields, you get an inductive energy. Everything is lagging, but the power companies require them to have a power factor above a certain point in order for them to minimize the cost of sending the power to them. Now, the reason that's the case is because the closer the power factor is to 1, the less voltage from the power company does it take to drive the same current. You'll just have to go with me on that one if you don't see it yet. Anyway, this is an old saying, so remember that lagging, the current, the actual current, the angle is behind the voltage. Now here's a specific example for this one. Please be attentive here. For this one, they give us 120 watts, right here, kilowatts, that's being used. Y'all follow me? And you'll notice the voltage is an RMS, unlike peak. So if you think about the formal definition, it says that PAV, right, was equal to VRMS, IRMS, and then it was times the cosine of theta V minus theta I. Now that is the definition of power factor, cosine of theta V over minus theta I. Does everybody follow me? So here, I can say PAV is equal to VRMS, IRMS, those are just magnitudes, no angles or anything, and times the power factor. So if we want the value of IRMS, the magnitude, this is only the magnitude, and I have PAV and I have VRMS, I divide it by the power factor and I can get IRMS. Or IRMS is simply equal to PAV, and then it's going to be divided by VRMS times the power factor. Now for this one, I'm not trying to go fast, I'm just trying to make you see this obvious. It's fairly obvious if you've done it. Here we got 120 kW, so it's 120 times 10 to the third, divided by 480, that's the magnitude of the voltage, and the power factor is 0.84. So now we have the magnitude of the current. Can you tell me what that is? Anyone? I could look, but I feel like asking anyone at all. If you got a calculator, just do it. Whoever asks this question, you picked a great one. This is a good question. It really showcases everything I want to talk about today, and it does it in a way that makes you, before I just talk theory, it gives you a question in mind. How do you do this? 297.62. Anybody confirm that? 297.62? So it's 297.62 amps. That's only the magnitude, and it's RMS too. Do y'all follow me? Now to get the angle, we have to go up here. You see we have a cosine of theta V minus theta I is equal to 0.84, right? So that means if here I'll put it here, 0.84 is equal to cosine of theta V minus theta I. So if you take the inverse cosine, I always put a cosine, but I'll do it cosine minus 1 of 0.84, you're going to get an angle which is technically theta V minus theta I, but it could be plus or minus this. But what is the inverse cosine of theta V minus theta I? Can somebody tell me that? Anyway, if you have a calculator. in degrees? You got it? Anyone?
32.86.
All right. So it's 32.86 degrees. I assume it's degrees. Is that right? Now, it could be plus or minus that. In other words, this theta v minus theta I could be plus or minus that angle. So the way we get the angle is it says it's lagging. And I know the voltage here is at 0 degrees. Do you all see this? That means the current has to be behind it by that angle, or the actual current will have this magnitude, and the angle will be minus 32.86 degrees. Does everybody follow me on this class? If you do, let me see your hands. All right? Make sense? Now what we're going to do is get the voltage at the source. Ask yourself how I would do that. Well, I have the voltage here, correct? I have 480 at 0 degrees, both angle and magnitude, right? But I don't have the voltage here. But now I have the actual current, I-RMS, don't I? Both magnitude and angle. How many see that? And therefore, I can get this voltage. I can say this voltage right here would be that impedance times IRMS. I'm saying it first before I write it. How many see this right here? I have the impedance, I have the current times impedance would be voltage. Everybody with me on this one? Please watch and make sure you see this. So I can say this voltage, and it doesn't matter, I can call it anything I want. I'll just call it V loss, doesn't matter. I'm going to say V loss here. Notice how I put the plus here. That means I'm getting plus, the current's going in this way, coming out that way, so plus to minus would be the orientation of that, and that means it's going to be IRMS times 0.1 plus J 0.2. IRMS, get your calculators out, make sure you don't mess these up. Here's something that people mess up. One of the numbers is going to be in rectangular, the other polar. People mess this up, and I know this. So it's 297.62 at an angle of, here it's going to be minus 32.86 degrees. And it's that times 0.1 plus J 0.2. So I want that value. Now I'm asking you to do it in your calculators for your sake. If you can start using your calculators in class, it will reduce the number of silly mistakes you make on quizzes. They will hurt you in this area. Just being unfamiliar with how to do these calculations will get you. Anyone? The polar's fine, rectangular's fine. Anybody? Just take 297.62 at an angle of minus 32.86 degrees times 0.1 plus J 0.2. I'm betting a lot of you don't know how to enter that in your calculator. Now's the time to learn.
66.55 at an angle of 30.57.
Say it again, sir.
66.55 at an angle of 30.57.
That's VRMS. Anybody confirm that? You get that? You get that? Okay, I'm going with it, all right? With me. All right, now, the next thing I'm going to do is going to get the voltage at the source, right here. So if I want the voltage at the source, I start the negative terminal. This is the way I always do it. I'm going around. It's an increase of 480 at 0 degrees. Do you all see this, class? How many do it? Can you see it in the back? Far back? So I get 480 at 0 degrees. An angle of 0 degrees. Remember, this is something, these are complex numbers. Magnitude and angle are real and imagined. Then I've got an increase of plus V loss, which is plus 66.55 at an angle of 30.57. So what's that gonna be? Now, this is gonna be a magnitude and a phase. I want magnitude and phase. Anybody?
538.4.
538.4.
Angle 3.6.
Say that angle.
3.6 degrees.
30.6?
3.6.
3.6, okay. Anybody confirm that? All right. Now, this is important. That's the voltage right here. And what's the current leaving this? IRMS, right? Correct? We know the angle of the current at this point, and we know the angle of the voltage, don't we, class? So we can get the power factor. Do you agree with me? How many see that? What is the power factor? Well, the power factor here at the source would be the cosine of the voltage at the source, which is, the angle of the voltage at the source, which is 3.6 degrees. Do you all see this, class? This is the important part. How many see this? Are you with me or not? Do you see it or not? You shook your head like no, you don't. All right. Do you know how I got the voltage at the source or not?
I got a different number for the angle at V loss. I got -19.
Anybody else? I was taking people's word for that. Because I'm looking at this right here. It could be negative. I'm not sure because this looks like it's greater than 45. I'm not sure if it's negative or not. Can somebody tell me this? Did you get this value? How many got this value? I'm kind of leaning on that way. Just listen for a second. Look at this one. All right, you see how J.2 is there, and then 0.1. Well, 0.2 over 0.1 inverse would be the tan. That's greater than 45 degrees, isn't it, class? Got something greater than 45 times something that's negative 32, or really added to. It sounds like it's right to me. It looks right. So if I take a look at this, the power factor at the source, now I hope, I don't know if you just check that, all right? Because I think there's probably something you punched in wrong, but I can't. What kind of calculator?
Yeah.
Any of you guys next to them got 84s? Behind you? In front of you? Oh gosh. Well, I'm going to go with this one. I think it's right. We'll find out in a second. So now it's the cosine of theta v, which is 3.6 degrees, right? Minus the cosine of theta I. Well, theta I is what? It's minus 32.86, so it's minus a minus or plus, right? Plus 32.86. And what do you get for that power factor? You're going to have to add 3.6 to 32.8, roughly. Call it 39 degrees. What's the cosine of 39? Anyone? Say again? I couldn't hear you. What is it? 0.80. 0.8. 804, did you say? Is that right? Is it lagging or leading, and why? I'm asking you now. Think. Well, the voltage angle is what? 3.6. The current angle is minus 32. Obviously, the voltage angle is ahead. Do you all see this, class? So it is lagging. The lag has to do with the current's location relative to the voltage location. You might say at the angular location. You all with me, class? How many see this? By the way, is that answer right? Who asked me this one? Is it right? Thank you. Did they give you the voltage at the source or not in that solutions?
Yeah.
They did? This is the way you do it. But here is the key to this. The whole key is getting the current's magnitude and angle right. The minute you see a load like this, now it's important you see this. They give you the power, average power, right? You know, average power has got to be equal to VRMS, IRMS. They give you V, 480. Y'all follow me? The line voltage. Then they give you a power factor. So now you can get the magnitude of the current from that, but you can't get the angle yet. You with me, class? Once you get the magnitude of the current, then you have to take the inverse cosine of 0.84, whatever the power factor is, to get the angular difference between theta V and theta I. And in this case, the voltage is at 0 degrees. If it is lagging, then your current angle is less than the voltage angle. If it's leading, the current angle would be greater than the voltage angle. That's the way you do it. If you do a bunch of problems on this, you won't mess up. But that's the secret to this stuff. Do plenty of problems and know how to use your calculators, because people can mess up on the calculators all the time right here. And I'm betting that what you just did, you probably found an error you can make on a quiz. I think they're right though. All right, so please make sure you just check that, because I'll level with you. I don't know 84s, I don't know any of that stuff, not TIs, but your neighbors around you do, and I'm betting they're right on that one, just by looking. All right, you good? This is perfect. So I got a question for you, all right? Now listen. So with this problem, I'm delivering 120 kW to the load. How much total power is being supplied by the power company over here? Call that the power company. Well, it's at least 120, right? 120 kW. You all with me? What else is responsible for dissipating power that's supplied by the power company? Anyone? You guys see it? Yes, sir.
The 0.1.
That's right. Now, if you want the total power, you would take, and now you don't need the 1/2 now. These are RMS currents and voltages. Now you take IRMS squared and multiply it by the resistance, 0.1. How much more power? How much power is dissipated there? Just take IRMS magnitude squared, so what is that? 297.62 squared, and then multiply it by 0.1. I asked this question, so how much is dissipated, and I'll call it P loss. Does everybody follow me what I'm doing here? It's just IRMS times, and this would be called R line, I think, in the book, but it's really the losses of the line. So what do we get for this? Say again?
8.86 kilowatts.
Milliwatts?
Kilowatts.
Kilowatts, okay. 8.86 kW. The total delivered is 120, so it's 128.86 kilowatts supplied by the source, which isn't bad. All right, that's not that bad, really. Now, here's the thing. As the power factor here at the load gets closer and closer to 1, the amount of power supplied by the power company, the percentage of power used by the actual utility or the load right there versus the loss will become larger and larger. That's the bottom line of this. You'll see more of this in a bit. How many understand this idea as far as power factor? Right? If you don't, we'll do some more. Did that answer your question, by the way? You got another one for me? That was a good problem. It's the way you do it, these problems, honestly. I can talk theory all I want.
746.
All right, hold on. All right, here's what I'm going to do. I'll do this one, then I'm going to do one with 2 loads instead of 1. Because this is, we're going to take the natural extension of this. For 746, this is a drawing in the book. And it's very similar to what I drew here. for the mechanical engineers in here, do you have a class where you have to do rotating machinery like internal combustion engines and electrical engines? I don't know when you get it, but that used to be a standard class. When you do that, you're going to find something these days probably that has to do with energy scavenging, where you're going to actually recover power from braking systems and stuff like this. And some of this that we're covering, well, it'd have to be modified, but it's applicable to that. One other thing I saw, I'm seeing these self-driving vehicles. Has anybody seen this thing? I think it's a Tesla. It looks sort of like a futuristic tanky coming down the road. Does anybody know what I'm talking about?
Cybertrucks?
What is it?
Is it the one with the sharp angles?
Yeah. What is?
Cybertrucks?
Is that Tesla or not?
Yes.
So what's the deal? It looks like it's armored.
It is armored.
Yeah, I think it's cool.
Yeah, there's been a lot of gunfire around here.
You gotta watch out for it.
I saw that thing. I'm like, man, I'm getting old. It's Back to the Future.
Fully reflective.
Solid stock price.
Those are some robots, and then the video of people controlling the robot.
Yeah, it looks
Because somebody's controlling them. Are you serious? Yes, they're on the wall. Are you serious? No, somebody was controlling the remote. There's a video of the people there in the box.
All right. Now for this one, so here's the thing they're asking for. They want this voltage at the source, and they want the power factor at the source. The key is always the current. Can you read it or not? If you can't, let me know, and I'll either write larger or I'll read it to you. It's just a simple circuit like the same basic out or template as the last one. Different values, you all follow? Now he's calling this in the book, he's calling this the lining voltage of the source. That's not the right, this is the source voltage. All right, so I put V source. I would not confuse you. I indicate clearly what I'm looking for. They want that source voltage and the power factor there, but the whole key is the current, right? Now, looking at that problem, this is the kind of thing you would get on a quiz. By looking at it, anytime you say kW, kilowatts, that is the average power, it's real power. And you know that PAV, right? We'll do it again this way. PAV is equal to VRMS, the magnitude, times IRMS, the magnitude, times the power factor, or time, I'm just going to put power factor here. We know it's the cosine of theta V minus theta I, right? So now we need the magnitude of the current. Can you all follow me on what I'm doing here and why? How do I get it? Can you see 40 kW here? It's a little small. So I have that, so I can take 40 kW, I'll put it on this side, 40 times 10 to the third. Then if I divide it by VRMS, which is 220, and then by the power factor, which is 0.8, now I get the magnitude of the current, IRMS. And what do you get for that?
227.27.
Say that one more time.
227.27.
0.27, and that would be amps. And now, how do I get the angle? Just think about it before I show you how. We covered it. How do I get the angle? Well, what is my next step? I have to take the inverse cosine of the power factor. That's the key, right? So when I take the inverse cosine of the power factor, which is 0.8, I get a value, an angular value. What is it? 30-some degrees. 36 point what? 0.85? 87. Okay, degrees, right? Now you tell me, if it says lagging, what is the angle going to be here? Negative, right? Negative 36.8. And this would be the current, RMS current. Everybody agree with that? All right, not done yet. How do I get the source voltage, magnitude and angle? We covered this. I know a lot of you know, you just don't want to say it. Well, what do I really need? If you look, this is just a line impedance, right? I've got the current now, I've got this current. So that means I have this voltage plus to minus here, don't I? That would be IRMS times this, or 0.1 plus J 0.3. Do you all agree with that? How many do? So let's go ahead and get this voltage right here, V source. That's minus the plus. So what would V source be? I'll put it here. Well, what would I do? The way I do it, I start the negative, right? We know the voltage around any closed loop sums to 0. I start here and I come here and I get a voltage increase of 220, right? At 0 degrees. Does everybody see this? It should be very obvious by now, right? So I get 220 at an angle of 0 degrees plus what? Which would be IRMS. I'm going to leave it as just IRMS there. Do this on your calculator. Let's see if you get the right answer. Plus IRMS. And here it's going to be times, and that's magnitude and angle, 0.1 plus J 0.3. So what do I get for V source? Let me have this number right here, just that number. Could somebody give that to me? Because I want you to be able to check your calculators. And gentlemen, you got a different number before? Let's see if he gets the right numbers. I'm making sure. So what do we get? If you just take IRMS, which is, what is it, 227.27 at minus 36.87 degrees times 0.1 plus J 0.3, what do you get? Magnitude and angle, if you don't mind. Go ahead and try it. I really am trying to help you. How many have made mistakes in your calculators doing calculations for tests? A lot of that happens. And it happens in a way that really irritates you because it's so obvious you made a mistake when you look back.
$71.87 at an angle of 34.7.
71.87 at an angle of 34, did you say?
34.7.
Okay. Now if you add that to 220 at 0 degrees, what do you get? Better be a positive angle. may not get, how many got that? Let's try that. Okay, good.
282.07.
282.07 at what angle?
8.34 degrees.
How many got that? Hopefully. 1, 2, 3, 4. I'm gonna go with that's the right answer. Everybody with me on this one? All right, let's keep going on this. Now I've got the current, magnitude and angle at the source, and I have the voltage, magnitude and angle. So what is the power factor at the source? Isn't that what he asked for too? Right? Power factor at the source is what? This is at the source. Cosine of what? Make sure you do it right. Cosine of theta V. Theta V at the source is 8.34, right? Minus the angle of the current, which is minus 36 or plus 36, right? 0.87. Now what's that power factor going to be, class? Anyway. 705. Is that right? How many got that? I hope it's right. All right, is it leading or lagging? Lagging, right? Look at the angle of the voltage and compare it to the angle of the current. The current angle is less than the voltage angle. Do y'all agree with that? And that's really what it's about. Okay. That problem, I think, is straightforward. Do you have any questions before I move on? Now, well, let me ask one more question. It's not part of it, but I would ask this kind of thing on a test or on a quiz. Oh, by the way, don't we vote on a test? Didn't somebody get the results? Aren't you supposed to send it to me? I might
Wednesday
remember
one.
discussing this. Let's try that. Remember on Friday? Didn't we discuss it? Did you get the poll out or not?
Someone else did.
Who did?
Wednesday won by a significant amount.
What?
Wednesday one.
It was honor made.
What? Wait, what?
I put the poll.
Could you email me that? And I'll forward this to everybody so I don't get blamed. Hey, look, it doesn't matter. I'm just trying to make sure everybody knows when the test is so we don't have any problems. I'm sorry, I didn't mean, I don't mean to. Is it Wednesday?
Yeah.
And did you forward it to me? I will forward it to everybody and I'll put it on OneNote. I will make sure that hopefully nobody misses it. Never can tell them. Okay, so here's the question, and this is the question that's not asked directly, but I will ask it. How much real average power is supplied by the source? Well, you know it's at least what? 40 kilowatts, right? But what do we have to do, class? I'm just doing this one more time to reinforce it. You have to take the magnitude of IRMS and square it times 0.1. Isn't that right? What would that be, by the way? So that would be the power of the loss. I'll call it P loss, which is going to be really IRMS squared times R, and this is R loss, the line. So what is that going to be? 0.1 times 5.2 kW? All right, so we had 40 kilowatts that we're using, but we had to have an additional 5.2 kilowatts from the source that we were actually providing an additional amount, which means you're getting some loss there that is, well, the power factor was 0.705. Usually they want it over 0.9, typically 0.95. And the way it works in the real world, I'm not a guy that does any of these power distribution things for Alabama Power. That's other people in this department. But typically for any kind of industry, they will tell you, you have to maintain a power factor, and they can monitor this, above, and we're going to see how you do that by using capacitors and parallel these things, a power factor of 0.9, usually 0.95, or they start paying the fine. And the fine is daily, and it's large. So that's the reason they'll make sure that they'll try to not have a problem. And I don't really know anymore. How many mills do we have around here? Do we have any? Do we have any large industry around here that does any kind of rotating machinery? Well, we have some automobile assembly lines and stuff. They may use some of these things, but we don't have the mills that used to have the big problem, because mills typically, they're all inductive motors, and those things are, it takes a lot of money for the capacitor banks to correct that. All right, now, one more thing, a little more complexity I'm going to do before I move on to complex power. The next lecture is going to be important that you're here. It's going to be a more confusing idea. But what I want to do is this. I didn't assign this one. In your books, there's problem 748. We're going to start this one, but I'm going to give you problems like this. And we'll be getting into something called complex power next class. So in 7.48, here you've got a power company. And then you have a line volt or line losses. And then you're going to have two loads. And the first load is 30 kW. And the power factor is 0.8 lagging. And the second one is 40 kW. And the power factor is, I better do it this way. Power factor is equal to 0.74 lagging. Now what they want is the same as the last thing. They want the voltage here, source voltage, and they want the power factor of the source. So that's what they're up to. Now, here, a little more complexity, right? We don't have one load, we have two loads, and they give you the voltage here. Sorry, I didn't put it here. This is plus to minus, I think it's 220, but 220 at 0 degrees. So now, how do you do that problem? Remember the secret to the last problem was what? The thing you had to get. Current. Now you got current, but you don't have one, you have two. You've got to get this current right here, and I'll just call that I1. And you've got to get this current here. Call that I2. And obviously this current, the line current right here, would be equal to I1 plus I2. I'm just showing you something, give you a little better idea of what we're talking about. Everybody clear on that? All right, so let's start with this one. How do I get this current? And again, remember, we have average power given. So remember, you know PAV is equal to VRMS times IRMS times the power factor. Do you agree with that? We're going to get the magnitude of the current first. So what's the magnitude? This is going to be for I1 right there. I can say that therefore I1, that current would be the average power, or 30 kW. It's divided by the line voltage, which is 220. And the power factor on that one is 0.8. Let me put that down right there. And likewise, I can also get I2 in the same way by saying it's 40 kW divided by 220. And there the power factor is 0.74. So if you could, this is just magnitude, we'll get the angle in a second. Is everybody following me why I'm doing what I'm doing? How many can see this and understand? All right. Now, what is this one in magnitude? I just need somebody to do the math for me. 170.45. And what about this one? We'll get the angle in a second. Anyone? 245.7. Now, how about the angle here? How do I get that angle, class? You know what I'm going to do is take the inverse cosine of 0.8, which is about 36 degrees, right? And it's lagging, so it's behind the voltage angle. The voltage angle is 0 degrees, right here. So this is going to be minus 36 point something degrees. What is it? Minus 36.5 degrees to 0.8? 87 degrees. What about this? Take inverse cosine of 70.74. Anyone?
42.27.
Minus 42.27 degrees. You'll notice magnitude and angle. Now to get this current, I'm trying to do this quickly because I think I have burned my clock down. I have to add them, right? Could you just add them for me? I think you'll see it at this point. I just want to give you, I mean, the solutions I'll put up, but I want to make sure you see what I'm doing. Does everybody understand the thoughts on why I'm doing what I'm doing? Okay. So if you add those two together, anyone? 415? All right. Minus what?
40.05.
All right, how many can take it from there? All right, we need to take that current multiplied by the line impedance to get the voltage there, add that to 220. Now we got the voltage to the source, then we get the power factor. I'm going to give you problems like this. Next class period, we're going to cover complex power. As much as possible, try to be here. It's a lecture that's important here for me. I've got to learn